I'm sure we all wish that we could be in person in San Francisco at this forum today, as we normally would be. But one benefit of taking things online is that our first two speakers are from out of state. They're in Kansas and Missouri, and we brought them on to talk about the research they've been doing on efficiency and toxicity of fires. And I think it's a really interesting and new perspective that I hadn't heard yet on how we can both protect our existing buildings and lessons learned to construct new buildings that kind of are multi-benefit. They're resilient, they're healthy, they're energy efficient, and they're fire resistant. So with that, Bob and Jeremy, I'll turn it over to you.
Hi, thank you. Bob, are you on?
I'm on. Thank you very much.
So we'll be talking to you today about some of the research that we've been doing over the past few years, and starting with thinking about first responders, and then moving into bigger questions about how we go about building our buildings and what that might mean.
We'll start by introducing ourselves. My name is Bob Renton. I'm with Henderson Engineers. I'm the Director of Forensic Engineering and Senior Code Consultant. We're a firm that does building systems design, and we have a rather large fire team, and we do consulting and life safety. A little bit of my background is I've been involved in the fire service in some way or another for the last 30 years, either line firefighting or code compliance and review and development, or now in administrative wings of it. I'm a fire designation with a fire marshal through the Center for Public Service Excellence. I've also spent most of my career investigating fires and explosions, and I'm a credentialed fire investigator with the International Association of Arson Investigators. I also have the credential for the Certified Fire Protection Specialist with the National Fire Protection Association. So seen fire and life safety and done lots of live burns from a bunch of different perspectives. So I hope we can bring something interesting to this discussion this morning. Jeremy?
Thanks. So I'm Jeremy Knoll. I work with BNIM Architects out of Kansas City. We also have a branch in San Diego. So I've been out quite a bit to see that office. I'm a lead fellow, so I've done sustainability projects worldwide for the past 16 years. I'm an architect and associate principal at BNIM, and then I also work with our local and regional climate action planning organizations. I'm on the executive board of a group called Climate Action KC, which, similar to Bayren, is about a 9 or 10 county area trying to take collective action. So this topic is something that really I will say came to me not in a way that I expected it to, but really coming from personal relationships and some conversations that we'll talk about in a little bit. So where are we in 2021? Why are we talking about this right now? What does this really have to do with where we're at and what we're trying to accomplish in our municipalities and in our careers and so forth? Wildfires are getting more intense and more frequent globally. I know Bob and I recently spoke in Tennessee and heard the statewide fire. It was his title, fire marshal.
I think he was the statewide fire marshal. Yeah.
Yeah. But to hear somebody there talking so much about how not even in terms of climate change, but in terms of the sort of boots on the ground and what it's taking to resource the fighting of fires as growing year over year, outside of a conversation of climate change was really it really struck home for me just how much this is becoming the reality for so many places, and so we're seeing fires grow year over year to where we now have essentially more than 7 months of risk compared to 5 months in the early 70s. And this is also a time when we're thinking really hard about the healthcare workers, the first responders, and essential workers as we recover from the global pandemic, and are thinking so hard about how important those groups are to us.
Thank you, Jeremy. So a little bit about what our agenda is for today. We're going to talk about what we have addressed as a problem, and originally our conversation started with cancer, the incidence of cancer in firefighters, strangely enough, and how those incidents and those health problems might be related to the environments that they're encountering while, in structure fires, and in the smoke and the soot and the debris that they're inhaling and being exposed to. So we'll talk a little bit about the problem, and then we've been done both theoretical and live burn research, and we'll bring some of that and discuss that in detail. And we'll obviously talk through the results. And then we've realized that there's several next steps that as this project of ours progresses, there's next steps and more conversations that we want to get into with a bigger group of people, and looping it in with the climate change and the wildfires. We were very excited to be a part of this conversation and to bring the little bit of information we have, and hopefully broaden some perspectives, and have a greater conversation. So the problem, we always think the problem begins with a question, and like I said, our question was, we saw the incidence of cancer and mortality rates in firefighters specifically. It continues to grow over the last 50 years, and both the incidence and the types of cancer. And our our question was, again, was from legacy construction in the 1950s to what we see in, well, when we started, 2020 seemed a long way out, but now we're past it actually. But the 2020 building systems and houses that we deal with are much different than we were dealing with in the 1950s. As far as lumber and synthetics and all the different components that go into them, and being tight and energy efficient, and all the insulation. So we wanted to know how the construction materials and the means and methods that go into those different components throughout those years, how that might contribute to the problem. So that's kind of the research we undertook, first from a theoretical, and then we went into some live burns and built different wall sections from different years, and we'll get into that in the details further. Jeremy.
Yeah, so part of what we were looking at is what are the decisions that are in front of us as an architect and an engineer every day? What are the things that we could start to look at and point to in our specifications and the way that we go about the design work that we do that could start to solve this? And so obviously the place to begin is in some of the fire code. So looking at ASTM testing, look at NFPA testing. Both of these offer a part of the solution, but neither of them tells us anything about what happens once a building is involved in fire, and the chemical changes that happen, what's happening in not just how much smoke is developed, but what is the chemistry of that smoke that both first responders running into a building are exposed to, as well as families and individuals escaping from a building are exposed to on their way out of the building. So that what we identified was that there really wasn't a test that looked at this sort of gray zone between these two. And so we developed what we referred to as sort of our Design to Burn 1.0, which was essentially facilitating cross-industry conversations where it was an engineer, architect, firefighters, and others in the industry all talking about sort of what, if we reach like the elephant and the blind man, what's the part that each of us can see and understand, and what's the part that we're touching, and how can we describe it to each other until we get a more complete picture of it. And then we went about presenting essentially this problem statement to these different regional and national conferences, trying to really gather information from others about this question. What are the choices that we make every day that could impact this result of cancer incidents in first responders? So continuing that research, then the next set of questions was, well, what do the sustainability experts tell us about this? We've got all kinds of certifications out there. These are just 3 of them that seem like they should tell us quite a bit about how to deal with toxicity in the built environment and in the building envelope. And so LEED certification gives us about 4 different credits dealing with material toxicity primarily, both in preventing toxic chemicals in coming in with the building materials themselves, as well as protecting the building from new sources of pollutants like oils on the bottom of your shoes coming in from parking lots and so forth. Well certification has several different credits that could be or measures that could be associated with this. Similarly, reducing toxins in the basic building materials. And then a couple that actually talk about wayfinding, because one of the things we learned from talking with firefighters is as you enter a building, if it's not a space you're familiar with, having really clear wayfinding means that you can get to where you're trying to go within the building more quickly. So there is some guidance within the WELL certification about how to set up a space that gives some logical wayfinding information. And then finally, the Living Building Challenge talks again about preventing those toxic chemicals from coming into the building in the first place, and sourcing those materials in a way that is going to benefit not just the people in the building, but the people down the supply chain. But if we look at all of these combined, what they're really doing well is they're dealing with material supply exposure to people in the material supply chain, exposure of chemicals to people during construction, and then exposure during occupancy of the building. But none of these really address or even begin to talk about what happens in an emergency, how the building changes during that moment. And I know, so I've worked on a number of K through 12 schools, and this was something that became pretty important as there was when I completed a few years ago here, had an electrical fire in a vault outside of the school on city property, but it dumped a bunch of smoke into the building. And so it was the better part of a week before they were able to safely reoccupy that space using all kinds of filtration and air testing before they could get back in. So it's not just about protecting people while the building is in operation, but thinking about what happens in an emergency like that and how do we continue to protect people. So another thing that the Living Building Challenge gave us, as I'm sure many of you know, is the concept, or at least a industry standard for what we call the red list, or the list of chemicals that are known to have harmful effects on both human physiology as well as the ecology in the spaces around us. Highlighted 4 chemicals in particular here at the top that are especially difficult to remove from buildings. Chromium-6, formaldehyde, halogenated flame retardants, and polyvinyl chloride, or PVC. And on the right, you can see just some of the impacts of incorporating these chemicals into our buildings. And this seems like an easy thing to say, okay, we're just not going to use red list chemicals. But when you start to look at even just the building products that and the furnishings that we put into our homes, we find these chemicals really everywhere. So what are the steps that we can start to take now to understand what we can do about these different outcomes, and how can we prevent them from coming into the building? And so, as Bob mentioned, this is where we started thinking about the idea that, well, maybe there's some fundamental parts and pieces to the way that we're building our buildings that could change, and what are the decisions that we could make about how we go about designing something like the exterior wall section that could begin to both give us some protection, but also some passively remove these chemicals and materials that we know that might chemically combine during a fire to create a toxic substance that doesn't exist in their inert form.
So that led us to many discussions. We spoke in different parts of the country and at different conferences, and it got us to more discussions with UL, with Factory Mutual, with USGBC, firefighters, lots of cancer research institutes and resources out there. And we realized that we needed to go for some applied research and to be able to test our theories and see if we could find some correlations. So we decided that the best way to do that would be to build wall assemblies or compartments at the time. So we ended up trying to wrap our heads around what we could do, and we looked for calorimetry, and we ended up at Oklahoma State University. We knew that we could get some use of a calorimeter there. So then we essentially put together a team. Henderson Engineers sponsored research with Oklahoma State University, and BNIM and Jeremy and Armstrong Forensic Labs, and then Turner Construction. We all came together and put our heads together and tried to, we knew what we needed to do as far as the different decades of construction legacy through modern, and we tried to micro analyze what we could. There's so many things to examine, so many things to look at. So we boiled it down to, we wanted to look at heat release rate and some fire dynamics, but we also wanted to get a lot of products of combustion and be able to analyze what's coming out of these different wall components. So we ended up, like I said, we sponsored a capstone project with the seniors at Oklahoma State University and their fire protection and safety engineering technology program. It started in January of 2019. And we sat down and we were going to do small scale. And then we talked about big scale. Our calorimeter was limited to about 2 to 3 megawatts, so we couldn't get too big. We didn't want to overrun the calorimeter. So we ended up doing corner wall components, and kind of modeled a little bit after NFPA 286's corner test. We looked to Dr. Armstrong at Armstrong Forensic Laboratories and their industrial hygienists to help us identify the different products of combustion that we could monitor for. So I'll let Jeremy kind of go through from an architectural standpoint what we decided on for the construction of the wall assemblies.
Yeah, thanks, Bob. So I've done quite a bit of residential construction and remodeling, both professionally and through volunteer work with the U.S. Green Building Council and an organization I founded and ran for about a decade called Historic Green, where we went and renovated historic homes in the lower Ninth Ward of New Orleans and in Kansas City, bringing them up to perform like new, sort of the most sustainable new buildings that are out there. So I'm pretty familiar with what's in the guts of these different homes and buildings from over these time periods. And so starting with our 1950s wall assembly, looking at those legacy burns, these were materials that were primarily things like plaster and lath. Often we'd find very little or no insulation in the walls. The wood itself in the typically 2x4 construction was a much denser wood than you could go and buy at like a Lowe's or Home Depot today. So much denser wood, and then often some kind of a simple tar paper over either a building sort of cladding boards or plywood material with a variety of types of finish on top of that for the sheathing. In each of these, we included a dryer vent running through the wall just to provide a place of penetration through the wall assembly. So you'll see that noted up above. And then as we get to the 2000s, this is where we start to see simply just fiberglass insulation filling a 2x4 stud cavity, 16-inch centers for the studs. Newer wood material, so faster growth wood that is much more porous. Then as we get into the 2010s, I actually based this plan on a LEED Platinum high performing building that will remain nameless. But this is a built wall section that I now wake up at night thinking about. And then based on everything we knew, again, we were starting this work back in about 2016, 2017. So 2020 seemed like we still had a little time to figure it out, but now our 2020s wall section is here upon us. And for this wall section, for both the 2010s and the 2020s, we went to a smart frame 2x6 stud spacing. For the 2010s, we used a closed cell foam insulation, a spray-in foam material. We actually calibrated the equipment using a board foam material, also of the 2010s assembly, which had some similar burn characteristics we'll talk about later. But then the 2020s, looking at things like mineral wool or rock wool as an alternative material for the insulation itself, knowing that it had a pretty similar price point, at least at the time that we were designing it, to the closed cell foam insulation. So we weren't talking about a big change in cost or assembly, but something that could potentially within reason, become a more standard building material type. And so then we worked with Turner Construction on actually building these wall corners. Initially, the students were going to build it, and Bob and I both shut that down pretty quickly. With these were students who had no real construction background, and we knew that we would get inconsistent assembly details and work. So we wanted a professional who builds homes over different time periods to do this for us. So they built it in a warehouse as a training exercise for some of their guys and gals, and then these were shipped down to the burn lab in Oklahoma.
And we kept pretty exacting details on how they were constructed and the materials, because we sense that we want to reproduce and be able to test on multiple different revolutions the same cells and the same products, obviously. So thank you, Jeremy. So then we went, and it became an idea of what are we going to sample for? Like I said, we knew that fire dynamics and heat release rate and some mass loss would be pretty simple, but getting into the details of the acids and the polynuclear aromatic hydrocarbons, the heavy metals that would be produced, the SVOCs, VOCs. So this was a collegiate project, obviously, and our budget wasn't unlimited, and our burn cell and our calorimeter was such. So we tried to maximize the most likely products that we would see in residential construction and fires, and what would be the most valuable for our study, and also what we could afford, because I mean, we could spend thousands and thousands of dollars analyzing the different components. So this chart kind of breaks down where the big components were that we were looking for and testing for, and then we and mostly the students, with some direction from Armstrong Labs, built the sample trains, and that's kind of what you see there. On the left is the calorimeter in the hood, and you can see our load cell is down there on the very base, and then our wall assemblies are basically two 4x8 walls that are joined at a 90 degree. And then we have a propane burner in the corner that is doing 160 kilowatt fire to ignite the wall assembly. So we did
NFPA corner test, right?
Yeah, there's NFPA 286 room corner test. It models after that. We wanted to be consistent and be able to be reproducible, and that seemed like a fair way to do it. We did 5 burns over 3 different sessions down in Stillwater, Oklahoma, and then sent the materials, obviously, in 3 separate samples back to Armstrong, and tried to perfect along the way our testing and our monitoring of the samples. So next slide. So we obviously, this was a collegiate effort and wasn't totally in the private sector. So there were some limitations, and we're aware of that, and we're learning from those, and continually strive to do more testing. We recognize there's really no standard testing or sampling process for what we were looking for. So like I said, we put our heads together and collectively throughout the team came up with what and how we were going to sample. Limited resources as far as experience and equipment. The sample stream, this is the first time it had been done at Oklahoma State. So we had some issues with condensation and some heat up in our ductwork that diluted some of our samples a little bit. Stoichiometric ventilation in the fire. Obviously in a calorimeter, ventilation's pretty much unlimited. We realized that in the real environment, a room fire or a compartment fire, you have incomplete combustion and you have limited ventilation. So you have sometimes more products of combustion, more smoke. It's not nearly as complete a combustion. We would have loved to done a full compartment. Like I said, the calorimeter limited that, so we wanted to do full scale, but so we came back to our corner 4x8 corner. And then obviously we wanted to do multiple burns for the same generation to make sure that all our data aligned and was accurate. But obviously with budget and laboratory time and the academic calendar, we ran one burn of each cell. So those were our limitations. But it's with anything, you have to kind of limit where you're at and what you can do. So we did 4 burns. There's 4 different cells. From the left to the right is 1950, the 2000, 2010, and 2020. And the chart in I should say we had to we punctured the wall during every 15 minutes. We did every burn for an hour, and then every 15 minutes we would make a controlled puncture in the wall to make sure we got heat and fire into the wall assembly. So you can see the first puncture, second puncture, third puncture. Those are 15-minute increments, and then the last is the extinguishment. And our biggest heat release rate ended up being the 1950s. We had the most consumption of that cell, and the lowest heat release rate was in the 2020s, and we'll go into better detail about that, but very little of that cell burned because of the construction means and methods. So we could spend all day looking at the heat release rates and analyzing that. It could be its own. We also looked at carbon monoxide and carbon dioxide production. And again, the blue line is the 2020s, and it's pretty baseline. But the green, which was the 1950s, and then the 2010, we had some really interesting peaks for CO and CO2 production. And then this is just one snapshot of the analysis that we got back from the sample trains and the analysis from Armstrong Labs, but just the different components and different byproducts that came out of the burns. And again, from it's color coded for each era of the burn cell. So green is 1950s, orange is 2000s, yellow is the 2010, and then blue is 2020. So we have lots of good data from that as far as products of combustion and the different chemicals that are offset from each of the wall cells.
So we're briefly going to run through each of the burns. I realize we're coming up closer to time here, so we'll try to get through these. I've already described how the walls were assembled, but now you can see on the bottom left, these are the measures that we tried to put each of the wall burns to understand what the different characteristics were. So looking at installed cost, what did it cost essentially per square foot to build this? What's the energy performance of it, R value, and how it would perform in the real world? What's the installed toxicity? In other words, what is a construction worker exposed to as they're installing this assembly? What's the heat release rate? How much heat is it releasing over that burn? What are the products of combustion? So what all in that assembly actually is able to be burned? And then how toxic is the smoke based on our measurement? So I will say that the 1950s burn was the most like being around a campfire of all of these. It did eventually start to burn hotter and hotter, but definitely it was cedar. It had a nice smell to it, and was ultimately a burn that you could mostly be in the room with. Whereas later, when we talk about the 2010s, we essentially had to get out of that space because it got so hot at different points.
The lumber that went into this wall assembly was from a barn in the 1940s, so it was nice, dense lumber that it held up really well in the fire, but obviously the cedar lap siding was almost totally consumed.
Right. You can see our the heat cameras on the right-hand side, and then on the left is essentially a thermal bridging analysis of the wall section itself. So we see that the calculated R value is only about 3.78 in this case, where we can see pretty clearly those studs becoming big thermal bridges through it, and then through the heat images on the right, you can see that it's pretty transparent to the fire. Really, everything in this assembly was consumable for the most part, with the exception of the drywall that we used on the interface. For our 2000s assembly, this was really just based on kind of a suburban typical assembly. The installed cost a little bit higher because it's got insulation, it's got these other layers for house wrap and so forth, composite siding, and a slightly more efficient stud assembly, but still pretty similar to what we were seeing in the 1950s. Still pretty low installed toxicity, because even though the fiberglass has at that time would have formaldehyde in it, your exposure to it would be pretty low as you're installing it, because you're not spraying that fiberglass in, you're putting it in bats. The heat release rate is a little bit lower here because we are protecting portions of the combustible materials. The products of combustion do go up though, and the smoke toxicity does as well. Anything to add on this one?
Yeah, we had a little less consumption here. We had some of the fiberglass insulation protected some of the wall space, and the oxygen interface within the wall was a little more reduced. So we didn't have near as much consumption as we did in the prior cell. But go ahead, Jeremy. As far as there, go ahead.
So our 2010s, like I said, just burned really hot and really fast. This was somewhat more expensive to install. And you can see the energy performance was quite a bit better. Again, this was from a LEED Platinum high-performing building. But the installed toxicity, the exposure of workers as they're spraying, the foam insulation, the heat release rate, the products of combustion all go up. And you can see that by the end, the only thing holding this assembly up was the cement board siding at the end.
Go ahead, Jeremy.
Yep. And so finally, the 2020s wall, which was packed with our with mineral wool in the wall assembly, you can actually put your hand on the outside of this assembly during the burn and not feel the heat coming through it. It was cool to the touch on the other side from the fire. Energy performance similar to the other one. Installed toxicity much lower. There was really very few to no redless chemicals at all in this assembly. And then frankly, it was hard to get it to burn. And for what burn we did achieve, it only burned away about 1.5 inches of the studs. So when we were done, we actually pulled the bat out and the wall was still structurally intact, at least as we would expect it to be able to escape the building.
Yeah, the heat and the smoke, just there wasn't much room in the wall cavity to have that smoke heat interface and have combustion occur. So it was just like Jeremy says, the first inch and a half of the wall stud, it was all that was charred.
So finally, here's our, as we looked at each of these, what was our sort of score for each of these, and what did we see? So installed cost, we see the 2010s and 2020s being pretty similar. Energy performance, the 2020 was actually a little bit better because we filled that entire cavity and had some continuous insulation on the outside. Installed toxicity, the 2010 was just off the charts for that, as well as the heat release rate, because the foam insulation in there was essentially like a frozen gasoline. So once fire got to it, it went quick, and like I said, was pretty unbearable to be in the room with that burn. But our focus today though is on this energy performance and installed toxicity, and so as you can see, those are the pieces where we can start to see the relationship as we tighten an envelope and allow air to move less and smoke to get out of the space. We see some big impacts here, but I think there are solutions going forward that offer us a way to be both energy efficient and to reduce that toxicity and exposure to residents. We did, working with the BayRen team, we looked at all of the housing in the Bay Area. So you can see on the left, the percentages is the total percentage of housing that's in that county. So Alameda County, for example, has 20% of the total housing of the counties listed here. And then across the right, we've listed the percentage of that housing that is from each of these eras. So something that can tell us is about if we have so much housing that needs to be renovated, if it doesn't have insulation yet, maybe this gives us some good information to act on in terms of giving preference to something like a mineral wool over a foam insulation. So next steps, setting a replicable standard. That's really what Bob and I are up to now, trying to grow this conversation. Here we are talking to you today about this. We want to refine the test methodology. We've got some good proof of concept here in our testing we've done, and then beginning to work with LEED, WELL, and Living Building Challenge to address this gap in the systems and develop a pilot credit or an innovation credit approach so that we can create a replicable way for others in the industry to address this.
And we seem to think that the wildland interface code and a lot of what's going on, and obviously in your counties, is of interest. The hardening of the different products that are utilized in your jurisdictions, it seems to correlate to some of what we've seen as far as the products of combustion and things being a little safer. And then I think there's also a good conversation here for sprinklers, both in the residence. I know most of your fires are coming from the exterior of the wall assembly rather than ours from the inside, but bottom line is it's burning and it's still off gassing and producing products of combustion that are harmful. Sprinklers, both inside and outside, are obviously they're essentially green. They're going to limit the size of the fire magnitude, which is going to reduce exposure from firefighters and occupants. And hopefully it's going to keep the products of combustion out of our ozone and help limit some of the global warming and some of the impact to our climate. So where do we go from here? Like Jeremy says, we just want to continue the conversation, and we want to continually share what we learn and any of the information we can provide. But we're also want to have more conversation and listen to what other folks and other experts have.
We'll stop here. If there are any, Emily, if you want to take back over.
Sure. So we're going to go into our Q&A now. Let's see if I can. Sorry about that. Yeah, we'll go into our Q&A. I have, if you want to stop sharing, or you can stay on that slide. Got some questions from the audience and sort of some predefined questions. I guess the big one is, we talked a lot in the beginning of this session about wildfires. When I heard you guys speak, I know that this was talking about interior started fires. So can you just elaborate a little bit more on kind of the lessons learned and overlap of what we can see or maybe deduce based on what would happen with these same wall assemblies if there were kind of ember intrusion or something beginning from the outside going in?
I think the same components are going to burn, whether it's from the inside or the outside. You still have the heat impingement and the ignition of those components, whether it's the wall stud or the insulation, inside or outside. I kind of touched, but the ventilation obviously is going to be different on the exterior. You're going to have unlimited ventilation, and it might burn quicker and maybe a little cleaner actually, because it's unlimited combustion, where if it's inside and you get incomplete combustion, you have more products of combustion and a darker smoke and more particles. So I think the chemistry is similar. So the ventilation's a little different, but bottom line is you're still burning the foam insulations or the wall studs or the barriers that are on the exterior underneath the exterior sidings. Jeremy, do you have any?
Yeah, I was going to say that the exterior siding does make a difference in that case. I mean, certainly we saw in that 1950s burn where we were using a cedar shingle siding that it all burned away, whereas in the 2010s where we had gone to a cement board lap siding, that was really all that was holding the wall together at the end. So the combustibility of that exterior cladding does make a difference overall for if the fire is coming from the outside, certainly.
And I'll reflect the fire hardening that I see you folks doing with the non-combustible, whether it's stucco or some cement-based product on the outside. That's obviously going to slow the heat spread, and it's going to slow the ignition. We did have trouble sometimes getting the fire and the heat into the wall assembly, and that's why we did the punctures every 15 minutes. And that's why we had the laundry vent in the exterior. So it sounds like if we can eliminate any of those openings in the exterior, whether it's a dryer vent or whether it's a soffit vent or a ridge vent, those are all going to help keep the fire and the heat out and reduce your chance of ignition.
You're muted, Emily.
Yep, this is what happens right when you try and screen share and look at the Q&A doc at the same time. So I'm just going to not screen share. Can you tell us if you think there's any, you guys are both work out in the Midwest. Do you think that there's any Midwest kind of building styles or adaptations or things that you have learned from your kind of natural disasters like tornadoes that you think could be applicable to California construction as we face more and more wildfires or other climate change related issues?
I mean, certainly, yeah. I think we can, especially thinking about resilience, wherever we are in the U.S. or in the world, there is some type of natural disaster around us that we need to account for, whether it's rising sea level or earthquakes or tornadoes. The solutions do look somewhat different, though. So certainly for tornadoes, it's about getting into an interior compartment that's hardened, where you can be protected from flying debris, so no windows, things like that. You want hardened corners so that even if the house blows away, you've still got sort of a room left there. The ideal for that is to have a basement you can go into. Whereas if you're talking about wildfire, I think really the strategy is both thinking about what Bob and I have talked about today, which is like what is in the walls of the building you're building. What's in the furniture that you're bringing into the house, if you're a resident or an interior designer for that matter, but then how does that play with the wildland fire code and how close you can plant plants right up next to the building, and how does that affect the survivability of the home in itself? So I think while we might not see the exact same building patterns, I think the approach needs to be holistic wherever you are.
And I'll say, yeah, we have wildland interface, but just on a much different scale. We have thousands of acres of open prairie land and then an occasional 3 or 4 buildings, but our density is so much less. So we encourage people to have non-combustible external construction and a barrier of combustibility between the house and the prairie and the grass and the combustible vegetation. But if we have one structure ignite, we don't have dozens of them that continually exponentially grow and create that firestorm effect that you guys have. So it's the density is where it's different here.
Great. Can you comment on how this research or how you hope the research will influence how well and living building challenge or other rating systems address materials?
Yeah, I do have a lot of thoughts on that. I think what we're already seeing is move towards material transparency. What I still feel like I am hoping to see within the next couple of years here is some better alignment between those systems on how to measure what's going into the building in a more consistent way. But certainly talking with them about this question and sort of this population that's for the most part I think slipped under the radar is kind of a big deal. I would hope, looking into the future, that we'd be seeing more buildings that are using less and less toxic materials in the first place. I would hope to see a new standardized test of some kind, whether it's an ASTM or UL or what have you, that does take into account the toxicity of the smoke, not just the amount of smoke developed. And then finally, thinking especially about first responders, a picture I've got in my head is the idea that a firefighter could go to a building and look at the fire control panel, open it up, and have similar on laboratories where you list all the chemicals that are stored in the building in tanks, having that same chart that tells you what kind of products of combustion are in the space that they're going into, so that they have an idea of how they should go about protecting themselves going in, whether they should be wearing hazmat suits or and extra filtration on their breathers, how they should treat the soot that's building up on their suits coming out. But I think all of this begins with creating a replicable method for others in the industry to start to measure this or deal with it in some way.
Next big question, since you mentioned it, how do we get people to move away from foam insulation? Because even if it doesn't ever burn, we know that there's still a lot of kind of issues with it and its sourcing. But then tied into that, I know when we spoke earlier, you also mentioned the embodied carbon impacts of mineral wool. So can you talk a little bit about those different insulation options and what really is best?
Sure. So one of the next battery of tests that I plan to run, looking at those four wall assemblies, is looking at the embodied energy in each of those, because the mineral wool is very, very high in terms of the emissions associated with the production of that material as compared to most foam insulation, since the foam insulation is 99% air, and a portion of it is also terrible fire retardant that doesn't do anything to actually stop a fire. I don't know. I mean, I think it's going to be conversations like this. I think it'll be more testing, like we're showing, to get more people like yourselves aware of the concerns and issues with the use of foam plastics. I mean, as a green builder, I will say that I don't know that I can always turn to this new assembly as something I can do, because the foam plastics, in terms of the building science, check so many boxes all at once, from moisture control to air tightness of the building to the R value of the building itself. So it solves a lot of problems. But my hope is that we would be at first talking about how do we protect it, and second, how do we replace it? Because as we've seen, by using hardened materials on either side of it, we do, and keeping essentially air flow from entering the wall cavity, that actually does quite a bit to help mitigate the opportunity for it to get into a condition where it's going to burst into flame. But when you're talking about a really hot fire, that can influence the spaces around it in a way that would work their way through that system more quickly. And I don't know, I think it'll take steady work and education throughout the industry, and an understanding of really what's going on with it.
We still have a lot of questions in the Q&A, which is great. So I'm going to close, I think, with one more, and then if Jeremy and Bob, if you don't mind, maybe trying to answer the unanswered ones.
Absolutely.
That would be great. But what I'd like to close it to kind of bring us back to our theme is, where do each of you think the greatest intersections for fire preparedness and energy efficiency? Like, what are those? Where will we really get our biggest bang for our buck if we, have a strategy that addresses both? And where do you think that they might conflict with one another?
I think we're on the right track. I think with the code that the wildland interurban, I can't speak anymore. The wildland urban interface code and the other codes that are out there, I think we're all coming together, both as AHJs and as jurisdictions and fire departments and developers and all the different products and businesses that bring all these components in. It's a consensus product. I think we're coming together. I think as we raise awareness through opportunities like this and others, it piques people's interest. And I think the more we learn and the more we talk and communicate and have this conversation is where that intersection is the most beneficial.
Yeah, I'd agree with that. I mean, I don't feel like we have the room to back off of the things like airtightness and insulation values that we're trying to attempt at this point based on our energy use. But at the same time, we need to be working on this. So I would say that focusing on the installed toxicity, really thinking about what chemicals you're allowing into the building in the first place, is probably the most straightforward place to begin to approach this. Bob also really briefly touched on sprinklers, and there's a whole section that we left out of the presentation all about residential sprinklers and the impact that they can have on suppressing a fire before it really involves the whole building. And thinking about the opportunity when you've got a fire coming from the outside of potentially even sprinklering the eaves of a building, so you're cooling the outside of the building, maybe with a dry sprinkler system or something like that. Might be worth exploring there. In terms of the conflict, I think we've been pushing more and more towards tighter and tighter buildings. And so the result is that when you have smoke building up in a tight building, it has nowhere to go. So thinking about how we ventilate in an emergency, whether it's having like a whole house fan that can kick on and essentially suck all the smoke out of the building, rather than having a fire department have to cut a big hole in the roof to get the smoke out of there. Those are some steps that deserve some additional exploration, I think, because that is where we see the big conflict happening between the drive for efficiency and the exposure to smoke.
Well, thank you both very much. If you wouldn't mind, maybe staying on a few minutes during our break to try and answer the Q&As that are left over. And then since I don't think we got to see the slide with your contact information, that is going to be sent out when we send around the slides, but if you could drop that in the chat for the participants, that would also be great. So thanks, Jeremy and Bob. We are going to take a 10-minute break, and then we'll come back with the second half of the forum, which is going to hone in on California specifically and the Bay Area.
Thank you very much.